Welcome to the first lecture video for Chapter 4. In Chapter 4, we're going to be studying the Laplace Transform method for solving differential equations. This is a really interesting method, and it's used to solve more difficult differential equations. In Chapter 1, we learned how to solve first-order differential equations with variable coefficients, and we had several methods for doing that. In Chapter 2, we looked at higher-order differential equations with constant coefficients, and we solved those with the characteristic equation. That was a pretty simple method. In Chapter 3, we briefly looked at solving differential equations with the power series method. That's a pretty tough method. And so today we're going to be looking at solving differential equations using Laplace transforms. In section 4.1, we're looking at Laplace transforms and inverse Laplace transforms. Our focus in 4.1 is not yet to solve a differential equation, but just to understand this new process of finding a Laplace transform. So our goal today is to learn the technique, and then later we will apply it to solving differential equations. So let's go ahead and take a look at how to find a Laplace transform. Part 1, Introduction to Transforms. Now, believe it or not, you already know how to find a transform. You know two specific transforms: differentiation and integration, which you know well, are two examples of transforms. These two operations change one function into another function. That's basically what a transform is. For example, f of x equals x squared is transformed into a linear function under differentiation. X squared has derivative 2x, so I'm converting one function into another function. That's called a transform. And to a family of cubic polynomials under integration. If we integrate x squared, we end up with x cubed plus c, or a family of cubic polynomials. So we're transforming a quadratic into a different type of equation. That's called a transform. Both of these transforms exhibit a linearity property. The derivative with respect to x of a times f of x plus b times g of x, notice right here we have a linear combination of functions. This is equal to a times f prime of x plus b times g prime of x. So notice the transform is applied to the function, and we have, first of all, the derivative of a linear combination of functions. Now we have a linear combination of the transforms. Similarly, under integration, if we want to find the integral of a linear combination of functions, this is also the linear combination of the transforms. The big F represents integration, the big G represents integration. We're going to see this with Laplace transforms as well. That is, a transform of a linear combination of functions becomes a linear combination of transforms. That feels like moving a constant out in front of a differential operator to differentiate the function of x, or moving a constant in front of the integral sign and then integrating the function of x. So at this point, you know two basic transforms, differentiation and integration, and both of those are linear transforms. We're going to see the Laplace transform behave similarly. Let's define the Laplace transform. Definition: let f of t be a function defined for all t greater than or equal to 0. Remember, the upside down a reads for all. Also notice we're looking at positive t values. That domain is going to affect some of our transforms later on. The Laplace transform, big F of s, notice we went from little f of t to big F. When you go from little f to big F, that indicates an integral has occurred. Also notice the argument here is t, the argument here is s. So we're going from one variable to another. The Laplace transform big F of s is defined as big F of s equals, here's some other notation for the Laplace transform. And by the way, when we write it by hand, we make a script L. That script L is unavailable on the software that I use to type the math. So you're going to see the L look like that when it's typed, but when we write it, we're going to write it as a script L. So big F of S is equal to the Laplace transform of f of t. And here's the definition. It's the integral from 0 to infinity of e to the negative st f of t dt. So the function that I'm trying to transform, I'm going to multiply it by e to the negative st in the integral. And notice we're integrating with respect to the variable t. So the variable of integration is t, and s is a parameter. So the s that I see right there is a parameter. That means we're going to treat s like a constant during the integration process. It's like a partial derivative, but in reverse. Now, if this integral converges, it's going to converge to a function of s. So when I find the Laplace transform of a function of t, the result is a function of s. All right, let's give it a try. Let's find the Laplace transform of 1. You got to start somewhere. We're going to start small. So we're going to find the Laplace transform of the function 1. Following the definition stated above, this is the integral from 0 to infinity of e to the negative st times f of t, which in this case is 1, dt. So we're integrating with respect to t. Now, this is what we call an improper integral because it has an infinite upper limit. So we're going to make it proper using a limit operator. Make sure when you're doing your homework that you show this part. This is good mathematical reasoning. We don't want to skip that step. Limit b approaching infinity from 0 to b of e to the negative st dt. That limit operator makes this part a proper integral. Now, we're going to integrate with respect to t, treating s as if it is a constant. So we're going to make a copy of the exponential function, and we're going to divide by the derivative of the exponent, which in this case would be negative s. And then we run that from 0 to b. Now, at this point, you have to remember that your variable of integration is t. S is a parameter or a number. We're going to treat it as a constant. So that means that the limits are going to get plugged into t, not s. So we're going to find the limit as b approaches infinity of e to the negative sb over negative s minus, plugging our lower limit in for t, we have e to the negative s times 0 over negative s. Now, remembering the exponential curve, if you have a negative exponent, I'll just sketch it out over here, the graph of e to the negative x does something like this, right? So as we move to positive infinity, the value of the function crashes down to 0. So the value of our limit right here, e to negative infinity, goes to 0. So that term is taken care of. And the second term is going to be 1 over negative s. We can cancel these two negatives. We're going to get positive 1 over s. And the limit as b approaches infinity of the constant 1 over s is the constant 1 over s. So we have just found the Laplace transform of 1. The Laplace transform of 1 is equal to 1 over s. So we went from a function of t, or in this case a constant function, to a function of s. The integral converged to a function of s. All right, so that was a pretty simple example. Let's beef it up just a little bit. This time, we're going to find the Laplace transform of t, still working from the definition. So we'll find the Laplace transform of t as the integral from 0 to infinity. Remember, this term is always there with Laplace transform, e to the negative st times our function of t integrating with respect to t. The first thing we need to do is convert it from an improper integral to proper notation using our limit operator. So we'll write this, the limit as b approaches infinity of the integral from 0 to b of e to the negative st times t dt. Now this integral is going to be a little more challenging. Looks like we're going to need integration by parts. We have an exponential function times a power function. So let's let u be the power function, u equals t, because t differentiates away to a constant, du equals dt. That means dv will be everything else in the integrand, e to the negative st dt, and we'll integrate both sides. Once again, we're going to get e to the negative st over negative s for v. So we can plug this in to our integration by parts formula, but don't forget about this limit operator out here. So we're going to evaluate u times v, that's going to be t e to the negative st over negative s. Now, that still needs to be evaluated, so I'm going to go ahead and put a little stopper here with our limits of integration, 0 to b. U times v minus the integral from 0 to b of v du. So we have e to the negative st over negative s dt. Voodoo, right? U times v minus the integral of v du. Let's go ahead and calculate this integral, and then we'll evaluate our limits together all at once. So we have the limit as b approaches infinity of t e to the negative st over negative s. Let's go ahead and make those two negatives a positive, and then we'll integrate with respect to t. So we're going to get e to the negative st. Whoops, we're going to get another negative, aren't we? We'll just stick it down there. There's already an s there. We're multiplying by s again, so we have negative s squared in the denominator. And we'll run that from 0 to b. Okay, next step, we'll plug in our upper and lower limits. Remember, since t is our variable of integration, 0 and b are getting plugged in for t, not s. Don't let that trip you up. So we have b e to the negative sb over negative s. Let's go ahead and make this minus e to the negative sb over s squared. There's our upper limit. Plugging in our lower limit, 0, we're going to have 0 e to the negative s times 0 over negative s. And again, still plugging in 0, e to the negative s times 0 over s squared. Okay, let's see what we can simplify at this point. Let's do the easy ones first. I'm looking at this guy right here. 0 times anything is 0. This one's also pretty easy. We have e to the 0 over s squared. So that top is going to turn into a 1. Right here, we're going to use the same argument as in the example above. If b is approaching infinity, we have e to the negative infinity here, and that also approaches 0. Now over here, we have a problem. We have infinity times 0. That's what we call an indeterminate form. Recall, if you have an indeterminate form, you have to rearrange it so that it is in the form either 0 over 0 or infinity over infinity, and then we'll apply L'Hopital's rule. So let's rearrange it a bit. Limit b approaching infinity. Let's call it b over s e to the sb. Notice now we have the form infinity over infinity. That's our green light for L'Hopital's rule. Okay, and remember, these two terms over here went to 0, and we have minus a negative 1 over s squared or plus 1 over s squared. Okay, now make the observation once again right here. The form that we have is infinity over infinity. Thus, we have the green light for L'Hopital's rule. And remember, with L'Hopital's rule, we individually differentiate the numerator and denominator. So I'm going to differentiate the numerator with respect to b to get 1. And in the denominator, differentiating with respect to b, we have 1 over s squared e to the sb plus 1 over s squared. Now, reevaluating that limit, we now have 1 divided by e to the infinity, which is 1 divided by infinity. That term now goes to 0, and we have calculated our Laplace transform. The limit of a constant is a constant. We can say, therefore, the Laplace transform of t equals 1 over s squared. So remember, our focus in this section is just to learn the technique, to learn how to find a Laplace transform. As you can see, it's pretty involved and pretty technical. So once we master this, then we'll actually apply this to solving a differential equation. Okay, let's try another one. Calculating Laplace transforms by definition. So our next example is find the Laplace transform of 8. That's what I like to call this problem. We're going to see it a lot. So Laplace transform of e to the at, or the Laplace transform of 8. By definition, this is the integral from 0 to infinity of e to the negative st times e to the at dt. Now, let's go ahead and combine our exponentials. Since we have like bases, we can add the exponents. So our exponent is going to be negative st plus at, but let's factor out a t and lead with our positive constant. So we have a minus st dt. Now, at this point, we actually have two constants. A is a constant, s is a constant. Our variable of integration is t, so we want to keep that in mind. And while we're at it, let's go ahead and make this proper using our limit operator. Okay, once we have that fixed up, then we can integrate with respect to t. So remember, when we integrate an exponential, we make a copy of the e exactly as it is, and we divide by the derivative of the exponent, which in this case is just the constants a minus s. And we're going to run that from 0 to b. Next, we'll plug in our upper and lower limits. Remember, that's called the fundamental theorem of calculus. So we're plugging b in for t, and remembering that a and s are just constants at this point. Upper limit minus lower limit. Okay, evaluating what we can. This term's going to be easy. We're going to end up with 1 over a minus s. Now, this term we're going to have to think about a little bit. We have e to an unknown constant times b, and b is approaching infinity. So the value of this limit depends on the sign of that coefficient. Let's look at a quick graph. If we graph e to the x, we get an increasing exponential function. And if we graph e to the negative x, whoops, missed my axis a little bit. Hopefully you get the idea. We get a decreasing exponential function. So as x approaches infinity, a negative coefficient would have a limit of 0 for e to the negative x, but as x approaches infinity, we would have a limit of infinity for a positive coefficient. Now, if this is positive, this guy's going to approach infinity, and that means the integral is going to diverge. So the only way for this integral to have a value or to converge to a function of s is for this to be negative. So let's go ahead and impose that assumption. Let's suppose that a minus s is less than 0. I'm going to write that down here. Let's assume a minus s is less than 0. We could solve that for s, and we would discover that means s has to be bigger than a. If s is bigger than a, that's a negative coefficient. And if that's a negative coefficient, then the limit would be 0. So we can add that in there. This goes to 0 with our assumption. Thus, we're calculating the limit as b approaches infinity of, this goes to 0. Over here we discovered we had negative 1 over a minus s. The limit of a constant is a constant. And I'm going to switch that around and call it s minus a. Just multiply the top and the bottom by a negative. The negative disappears from the top and our signs switch, and you can flip your terms around. That just makes it a little bit easier to read. So we can say, therefore, the Laplace transform of eat is 1 over s minus a, provided s is greater than a. Remember, if s is less than a, our integral diverges. So far, so good? That's called calculating a Laplace transform by definition. But I've got a little bit of good news for you. We're going to be doing lots of Laplace transforms of all kinds of functions, so we can also evaluate these by table. Now, if you will open the inside front cover of your textbook, you're going to see what we call a table of Laplace transforms. So let's look carefully down this list. Okay, on the left side here, we see a function of t. On the right of the column, we see a function of s, or the Laplace transform. So notice here, we've got the Laplace transform of 1. That equals 1 over s. That was the first one we calculated. The Laplace transform of t is 1 over s squared. That was the second one we calculated. And then over here on the right side, the Laplace transform of eat is 1 over s minus a. So we've got a lot of common functions that appear in differential equations listed here on these two sheets. And again, this is on the inside front cover of your textbook. It's going to be really useful when we get to actually solving differential equations. So we're going to work this next example by using that table of common Laplace transforms. One thing I want you to remember, though, is the linearity property. Since the Laplace transform is a linear transform, then we can say the Laplace transform of a linear combination of functions is the linear combination of the Laplace transforms. What that means is I can focus on transforming the function of t and simply factor the constant in front of that operator as you would with a derivative or an integral. So we have b times the Laplace transform of g of t. Okay, so remember that. That will help us with working our problems. Okay, let's give this a try. Find the Laplace transform of 4e to the negative 3t minus 10 sine of 2t. Applying our linearity property, we could rewrite this as 4 times the Laplace transform of e to the negative 3t, that looks like eat, the one we just derived, minus 10 times the Laplace transform of sine of 2t. And remember, we're not calculating the integrals, we're doing this by table. So we have 4 times the Laplace transform of e to the negative 3t. This is not only on our table of transforms, but we've got it right here. Notice the a here is positive, the a here is negative. So we have opposite signs for a. So if we have e to the negative 3t, we're observing that a is negative 3. So this is going to be 1 over s plus 3, right? 1 over s minus negative 3. That was a quick, easy Laplace transform. Next, we have minus 10. We're going to look up the Laplace transform of sine of 2t on our table. So sine of kt is this formula right here, and we have sine of 2t. So we're just observing that k is equal to 2. So plugging 2 in for k, we have 2 over s squared plus 2 squared, or 2 over s squared plus 4. Thus, the Laplace transform of this function is 4 over s plus 3 minus 20 over s squared plus 4. It's very fast and efficient on the table, and you're going to get used to a lot of those transforms, but you do want to be able to calculate them by definition as well. All right, let's move on to talking about when do we know a Laplace transform exists. We will briefly discuss the necessary and sufficient conditions for the existence of the Laplace transform. We're going to learn a couple of new definitions here. Here's the theorem. If f of t is piecewise continuous on 0 to infinity and of exponential order c as t approaches infinity, then the Laplace transform of f of t exists for s greater than c. So the Laplace transform of a specific function is going to exist if that function is piecewise continuous and of exponential order c. And you're probably thinking, what in the world does that mean? So we're going to take the time to define those two things. First of all, piecewise continuous. A function f is piecewise continuous on the interval from 0 to infinity if in any interval 0 less than or equal to a, less than or equal to t, less than or equal to b. This means that I have t on some finite interval, and notice t is still greater than 0. Then there exists, the backwards e we pronounce, there exists at most a finite number of points, t sub k, where 1 is less than or equal to k, less than or equal to n. So this is just saying that subscript is a finite number and it has a finite upper limit, at which f has finite discontinuities and is continuous on the interval t sub k minus 1 less than t sub k. Okay, did you get all that? Well, I'm going to explain that very simply with a picture. The picture will be a little less technical. So let's look at a graph of some function f of t that has finite discontinuities. That can be a hole, that can be a jump, but it cannot be an infinite discontinuity. An infinite discontinuity is an asymptote. So no asymptotes in our graph. So we're going to look at a couple of values on our t-axis. We'll call them t sub 1, t sub 2, t sub 3, t sub 4, etc. We're going to continue labeling points on the t-axis like this until we get to a general spot in here somewhere, t sub k, dot, dot, dot. Okay, now our function is going to be piecewise continuous if it has a finite number of discontinuities on any subinterval. So for example, our function may do something like that on the first interval, and then it may do something like this. We say that it is piecewise continuous. It may have a jump here as well, and this may continue throughout the entire graph. So it may start here, may go up something like this. And again, I'm just sort of making up the graph. So the idea is it is continuous on this subinterval, it is continuous on this subinterval, and it is continuous on this subinterval. And then from that point out, it's going to be some sort of continuous function. Okay? So we have a finite number of discontinuities. Got a discontinuity here as a whole. Got a jump discontinuity here. Another just jump discontinuity, so on and so forth. But on those subintervals, it is continuous. Now, this is going to help us when we get back to our spring mass systems. We're going to be turning our external function on and off, and we're going to do that with a step function. A step function is an example of a piecewise continuous function. The other thing we need to examine here is the definition of exponential order. A function f is of exponential order c if there exists constants c and m greater than 0, so positive constants, such that as t approaches infinity, we have the absolute value of our function is less than or equal to some multiple of an exponential function with a positive exponent. That's what it means to be of exponential order c. The graph of the absolute value of f of t does not grow faster than some exponential function me to the ct. Now don't get too hung up in these definitions. As long as you have a working understanding, you don't have to memorize those definitions word for word, but I do want to explain this using pictures. Pictures will make it make sense. So we're going to consider several functions of t. We're going to see what does it look like to be of exponential order, and what does it look like to not be of exponential order. So, for example, let's just consider a linear function, something like this. Linear function t, y equals t. This function is less than the function y equals e to the t. Since t is less than this exponential function e to the t, we say that it is of exponential order, and in particular, exponential order 1. We could also look at a decreasing exponential function, such as e to the negative t. It is of exponential order because it is also less than this function, e to the t. Another example, if we consider a cosine or a sine wave, any sinusoid, I'll just go with the cosine wave here. Cosine of t. All of those are of exponential order because each function lies below or is lower than an exponential function. So what would it look like to not be of exponential order? Well, an interesting function to consider for that might be something like e to the t squared. E to the t squared is going to grow faster than e to the t. So e to the t squared is not of exponential order. Okay, so not of any exponential order. Whereas the functions on our left, these are all of exponential order. And in particular, we're looking at the order 1. So in order for a Laplace transform to even exist, the function has to be piecewise continuous, and it has to be of exponential order. It can't grow too fast, otherwise the integral is going to diverge. If those two things are met, the Laplace transform exists, and then we can use it to solve differential equations. So again, don't forget our goal is to learn how to find Laplace transforms by definition and by table today. And we want to practice applying this to step functions. So part 3, let's talk about transforming piecewise defined functions. The step function is going to be very useful when we get back to our spring mass systems. So you may be familiar with this, it may be brand new. So I want to make sure that you have a working understanding of the unit step function. Here's the piecewise definition of our unit step function u of t. U of t equals 0 for t greater than 0 and 1 for t greater than or equal to 0. So if t is negative, the value of the function is 0. Except at t equals 0, we've got a strict inequality, so we'll make sure and put a hole there. For t greater than or equal to 0, the value of our function is 1. And because of the inclusive inequality, we're going to make a solid dot, and that's going to continue to the right. So this is what we call the unit step function. In some sense, we're going to interpret this later as when the value of the function is 0, we turn the function off, and when it is 1, we turn it on. So back to our spring mass systems, if we have some sort of external forcing function, now we're going to be able to model how to turn it off and on. We're also going to be transforming these unit step functions to the right and to the left. So let's make sure we understand when we have something like this. This is a horizontal transformation to the right by a units. So it's going to look like our original function, but it's going to be translated to the right by a unit. So we'll figure out a somewhere on our t-axis there. This has the value of 1. Whoops. Translate that to the right. Make sure I get my endpoints correct. That's going to be a hole. That's going to be a solid point. So the idea here is the function is off until we get to a. If we're looking at t measuring time, after a seconds, the function turns on. Okay? Now, the interesting thing is both of those unit step functions are piecewise continuous. And of course, they're of exponential order. That means their Laplace transform exists. So let's talk about how do we find the Laplace transform of a piecewise defined function. Example 5. Find the Laplace transform of f of t for f of t equal to 0 from 0 to 3 and 2 for t greater than or equal to 3. Let's just make sure we understand what that function looks like to begin with. I'm going to sketch a quick graph of f of t, not because we have to, but again, just for practice. So from 0 to 3, the function value is 0. Then at 3, the function value jumps up to 1. So let's draw that in here. From 0 to 3, we could say the function is off. At 3, it jumps up to have the value of 2, and then it goes on to the right from there. Okay, so it is a piecewise continuous function. Now, we want to find the Laplace transform of f of t. This is going to be the integral from 0 to infinity of e to the negative st dt. That was the definition of the Laplace transform. Now, we can break this up into two integrals. One from 0 to 3, where the function value is 0, and then from 3 to infinity, where the function value is 2. So this becomes the integral from 0 to 3 of e to the negative st. Now remember, the function value here is 0. That's going to be an easy integral to evaluate. And then we'll evaluate from 3 to infinity, e to the negative st times 2 dt. Again, recognizing that that first integral has a value of 0, then we can work on the second integral. We're going to rewrite it as 2 times the integral from 3 to infinity of e to the negative st dt. Let's go ahead and evaluate the antiderivative. And while I'm at it, I'm going to sneak a limit operator in here since we have an infinite upper limit. Antiderivative of e to the negative st is e to the negative st over negative s. And we're going to run that from not 0, but 3 to infinity, or 3 to b. Let's plug in our upper and lower limits in for our variable of integration, which is t. So we have 2 times the limit as b approaches infinity of e to the negative sb over negative s, minus our lower limit, e to the negative s times 3 over negative s. Looking at evaluating our limit, as b approaches infinity, e to the negative infinity goes to 0. And evaluating the exponent here on the right, we're going to have 2 times the limit as b approaches infinity of e to the negative 3s over s. Those two negatives are going to cancel. S is constant with respect to t, so we have the limit of a constant, and that gives us a constant. So the Laplace transform then is 2e to the negative 3s over s. So the Laplace transform of our piecewise defined function is not a piecewise defined function. I think that's pretty interesting. Laplace transform of the given piecewise defined function is 2e to the negative 3s over s. Piece of cake. Now, at the beginning of this lesson, we talked about how differentiation and integration are examples of transforms. In fact, they go together. Differentiation is the inverse transform of integration, and integration is the inverse transform of differentiation. So you can probably expect if we learn a transform, we're going to have to acknowledge its inverse Laplace transform. And that's how we're going to finish this lesson. If big F of s is the transform of some continuous function, then little f of t is unique. So when I find the inverse transform, when I go from big F of s back to little f of t, this result is going to be unique. Now, to do our inverse transforms, we're going to use our table of transforms. So notice we were going in the forward direction from left to right. When we look at a function of t, we found the transform function of s on the right side. Now we're going to go in reverse. So let's look at the nature of our function. Observe the notation. We're looking at the inverse Laplace transform. That means we're going from a function of s to a function of t. So we need to find a function of s that has this nature on our table. So examining our table, notice right here we have a power of s in the denominator. So I'm going to be using this pair right here. We have in our problem in the denominator s to the fifth. Now, what I want to do is make sure that it matches this pattern. If I have s to the fifth, that means I have s to the 4 plus 1, which means I need a 4 factorial in the numerator, but we don't have it. Well, we're going to introduce it and immediately cancel it out. So I'm going to rewrite this as 1 over 4 factorial times the inverse Laplace transform of 4 factorial over s to the 4 plus 1. Okay, the 4 plus 1 in the denominator is just to recognize that in this case, n is 4. The Laplace transform inverse formula requires 4 factorial in the top. Since we don't have it, we're going to multiply and divide by it. So essentially here, we're multiplying by 1. Thus, we have 1 over 4 factorial. That's 1 over 4 times 3 times 2 times 1. Now we can observe from the table, the inverse Laplace transform is t to the nth. Remember, n in this case was 4, so we have t to the 4th. Thus, the inverse Laplace transform is t to the 4th over 24. Okay, we can say, therefore, the inverse Laplace transform of 1 over s to the 5th is function t to the 4th over 24. So sometimes it takes a little effort to make sure that your function matches the form of what you'll find on the table, but once you learn a couple of tricks, it's really a quite simple operation. Okay, example 7. Find the inverse Laplace transform of 1 over s squared plus 7. Remember, we write the script L, inverse Laplace transform of 1 over s squared plus 7. Remember, when you're doing your homework and you're finding inverse Laplace transforms, use the table. So I'm going to look at the table, and we're looking for something that resembles the nature s squared plus 7 on the bottom. Now, look at this formula right here. We have 1 over s squared plus 7. I notice from this denominator, our particular problem matches that nature. We have square root of 7 squared, or s squared plus 7. So in order for the inverse transform formula to work, we need k in the numerator. And in the numerator in our problem, we have a 1. So recognizing that k is the square root of 7, we're going to multiply and divide by the square root of 7, so it matches that formula. It's going to look like this. 1 over the square root of 7 times the inverse Laplace transform of the square root of 7 over s squared plus 7. So we are multiplying and dividing by the same thing, essentially not changing the original problem, but now it is in the correct format that I can find the inverse Laplace transform, and we just get this multiplier in the wash. So we have 1 over the square root of 7. Let's check out what the inverse Laplace transform looks like. Remembering that k is the square root of 7, we have sine of square root of 7 times t. Sine of square root of 7 times t. Be really careful how you write that. Make sure that your t does not sneak under the radical. In fact, it's best to take the t and put it in front of the radical. So I'm going to write it 1 over the square root of 7 sine of t square root of 7. If you absolutely have to rationalize that 1 over square root of 7, go for it, but you can leave it unrationalized. Okay, one more problem, and we'll be done with 4.1. Find the inverse Laplace transform of negative 2s plus 6 over s squared plus 4. So notice the denominator, we've got the sum of two squares, and in the top we've got a linear function. If we peruse through our table, we're going to be able to find the sum of two squares in a couple of denominators, but we don't have a linear numerator, okay, with two terms anyway. So we're going to use a combination of these two formulas. So let's begin by separating this out using our linearity property. So I'm going to take each term of the numerator and split it up over the denominator. And while I'm doing that, I'm going to factor out constants. So let's start with putting negative 2s over the denominator. I'm going to factor the negative 2 in front of my operator and leave this as s over s squared plus 4. Then we're going to have 6 over s squared plus 4. We can factor the 6 out of the top. We have inverse Laplace transform of 1 over s squared plus 4. Now this first one matches this formula. So we'll be able to find the inverse Laplace transform of that first term. However, the second term requires this constant k in the numerator. So looking at, let's do one thing at a time. Let's go ahead and inverse transform this. We have s over s squared plus 2 squared. We have s over s squared plus 2 squared. So k is equal to 2. The inverse transform then is cosine of 2t. Negative 2 cosine of 2t. Next, looking at 1 over s squared plus 4. Remember, we need a constant in the top. If we have s squared plus 4, k would be 2, which means once again we need to invent and cancel the 2 in the numerator. When you multiply and divide by the same number, you don't change the value of the original function. So I'm multiplying by 2 and dividing by 2. This is now in the form that matches the table, and I can see the inverse transform is sine of kt, or sine of 2t. Let's reduce this to 3 and call that sine of 2t. Now at this point you may have no idea what a Laplace transform is for, but remember your focus is to learn the technique in this section, and then we will see how it applies to actually solving a differential equation. All right, good luck on your homework and thanks for listening.